is Professor John Wallace, also a member of Pierce since the inception of the center. He was a faculty member here at that time. His expertise is in reinforced concrete walls, field instrumentation, system identification, and a number of other topics. Heavily involved in ACI and its committees and moving research results into practice. I am glad to have had him as my colleague for over 20 years now, and his topic will be design and retrofit of buildings. John.
Thank you, John. And it's nice to invite you all to sunny Southern California, at least for tomorrow or the next day. This time is always a great time for reflecting. Northridge earthquake, I mean, almost to the day, I was just looking it up, I started my academic career almost to the day 30 years ago when I showed up in a classroom. It wasn't quite as nice as this, but there were about as many people. And it was quite a challenge. Now, Northridge came along about 5 years later and certainly changed my career. It's why I'm standing here, and John and I are colleagues, because it changed a little bit the path of UCLA. So it certainly had a tremendous impact on my career and the research that I have done. Now, okay, I can do that. I guess we can do this too, right? I don't know if I dare do that. So at any rate, today I'm going to get to talk a bit about, if I can hit this, very quickly observations, some accomplishments and some challenges. Now the observations I can skip over relatively quickly because between the previous speakers they've kind of punched all the same slides I'm going to have up here as well. So, but I wanted to put these up there because it's important to set the stage. I mean, first of all, there's retrofit. I mean, we observed that in terms of existing buildings, we had some serious issues that we had to look at. That was something that was abundantly obvious, whether it was columns or joints or walls and so forth. So that was a topic that certainly just came about at this time period, the problem with existing buildings. And another one is, a slab column punching failure for that Bullock's department store was certainly really interesting. We were very fortunate that many people didn't get killed just because of the timing of the earthquake. The other one that was kind of interesting was this idea of repair. Certainly, no one really at that time was very worried about repair. I mean, we had the San Fernando earthquake and a lot of code changes had developed in the 80s and 90s, and this was the first real test of kind of modern seismic codes. And we certainly found out that we were doing better with new buildings, but there were certainly some issues. Existing buildings and repair are certainly big problems. Diaphragms, Jack mentioned this quite a bit. The fact that we didn't really worry about designing diaphragms, and particularly these precast topped. And we were starting to do a wonderful job. We could detail columns that could almost bend over and touch the ground. So no one could tell me concrete couldn't be made ductile, but if you don't design the system and the gravity system is not compatible, the gravity system in this case, basically failure pulled down the lateral system. So we had this problem of compatibility. I loved looking a bit around to find something useful about redundancy. There are no good figures about redundancy other than all us academics that put 1 bay frames and then 2 bay frames and 3 bay frames. But nonetheless, that certainly became a topic of interest. The fact that we were starting to put all our eggs in one basket, and that's not a very good design philosophy. And it also it related to diaphragms, made them more complicated, and certainly nonlinear torsion became an issue once you started failing one side or the other. So there were these complications relative to redundancy. Norm talked about ground motions, and I think particularly as structural engineers, we became interested, or at least noted, that there were these issues with being closer to the fault. I mean, heck, when I started, California, basically, it was zone 4. Man, you didn't have to worry about anything else. It was simple. You looked up zone 4 and you found the Z, and I was always 1, and there was an S factor, and you were done. And so it was simple. I'm not sure we've come a long way with ground motions to partially answer John Bray's question. I mean, they go up, they go down, and I don't think in some ways in the ground motion side realize how we actually design buildings with R and CD and omega. The granularity isn't there, I think, often to worry about whether the ground motion's going up or down 20%. Wood structures. We certainly had the tuck under parking issue with soft stories. And as mentioned, there's wood houses. We had the problem with connecting to the foundation and cripple walls and so forth. And there is mentioned, there's some talks on that later. And then in steel structures, particularly issues with brittle fractures that were mentioned, brace fractures, fractures through columns and some brace issues. So the idea that steel was there were no problems associated with steel certainly came out, not immediately, but down the road. So, and there are other things that I didn't touch. Bridges, because they've mentioned, Jack mentioned tilt-up structures. Those are certainly important as well. But when you start looking at the wealth of information and challenges, there were a lot of them. All right, so now quickly just looking at, well, what have we actually managed to get done in the last 25 years? And certainly by Northridge, we had identified the need to retrofit existing buildings. And 25 years later, I think we still realize that the buildings designed by the last building code may still need to be retrofitted in some way. We keep finding problems that we need to solve, which is good. But looking at the progress that we've accomplished in terms of guidelines and the research available and the data available for existing buildings is actually quite remarkable. It was just starting in 1994. I mean, before that, it was like 75% of code, and in many cases, that's unfortunately what it still is. But we've now got guidelines. FEMA developed the series. We're down to FEMA, ASCE 41. And if you look at it now, I thought I had it listed here, but ASCE 41 is something like 550 pages. The 17 version is very detailed. It's slowly gone through updates, maybe slower than many of us would like to see, but certainly research is finding its way in there. So the development of the FEMA 356 and 273 and eventually ASCE 41, that's a huge accomplishment over the last 25 or about the last 20 years. Peer research. I mean, as mentioned by Khalid and Jack, that focus on non-ductile concrete buildings has had a big impact, and on performance-based earthquake engineering. Those type of concepts were just in their infancy in the mid-90s. So that's a huge accomplishment. And then there are ongoing projects for, say, ATC, trying to make sure that research we do gets integrated into practice a lot faster. I know when I started out going to one of my famous ACI 318H committees, before I was a member, I'd go in, sit down, and I'd watch Professor Maley try to present something and make a code change. And back in that day, it was further study was always the answer at the end of the discussion. Things seemed to go really slow, and as a young academic, it was very frustrating. Now I think things move along a lot faster, and that's kind of encouraging. Related to retrofit, it is also mentioned the effort of hospitals. I think our need, this SB 1953 really pushed us to become better at retrofit and to be maybe a little more creative. And in some of those, a few cases that I was particularly involved with was actually doing building-specific testing to try to come up with a more economical retrofit strategy for a particular building. In some cases, you could really save a lot of money. So this kind of integration that researchers and practitioners actually get together to try to come up with a better solution, I think is something that I've certainly enjoyed working on with many people that are in the audience and many that aren't. In terms of retrofit also, there's the seismic ordinances. This is a big deal. I mean, we've got the LA ordinance for the soft story wood and the non-ductile concrete. You can see that there are a number of other jurisdictions, Beverly Hills, Burbank, that cover the non-ductile concrete buildings. There's also Santa Monica and West Hollywood are looking at pre-Northridge steel moment frames. So this idea that we've got mandatory requirements, I think, is really important. It maybe is a little frustrating that it took 23 or 4 years after Northridge to accomplish that, but I think you also have to put it in context of how far we've come with analysis and retrofit approaches, and how much more educated our community is. I mean, most of the engineers that we're sending out of here at UCLA now are going out and working. I think that it's trickled down as far as the amount of education that is involved in all the different firms. Now, it will take time. So in LA, we're moving along into the 3 years after order, and we're making progress. And we'll just see how long we have before that big earthquake hits and how much progress we're able to make. But at least we're making progress. And we've got goals, and we're going to get there. And we hope we'll get there faster than 25 or 30 years. Time will tell. Accomplishments for new design. As I said, I've been heavily involved with ACI. I looked back at the 95 version of the code, and it had 24 pages. And it was kind of like about steel moment frames. There was not very much about anything in there. It was a great document, and even this 95 version had a kind of an emergency change related to gravity systems. But it was a fairly simple document. Well, we go to the 14 version. It's more than twice as long. It now has foundations in it. There's a lot of material in diaphragms. There's even more material on diaphragms in chapter, I think, 4. It's amazing the amount of detail, which is one of the reasons our engineers all need to get a master's degree in order to figure out a lot of this stuff. But certainly that's tremendous progress. The 19 version of the code, it has some very interesting material in it too, related to updates in seismic design. Then we've got new design and integrating performance-based design for new buildings. I mean, certainly over about the last 10 plus years, this has been a big accomplishment to actually incorporate sophisticated nonlinear analysis and design approaches into practice. So this is certainly a big deal. And one of the things I've certainly enjoyed is the collaborative part of what we do. In terms of retrofitting hospitals, this is the St. John's facility in Santa Monica that got demolished shortly after the Northridge earthquake. I worked on a somewhat similar project with KPFF and OSHPD to come up with a retrofit strategy that involved testing. And it was a kind of a big event in my life when I figured that it was really valuable to get out there and try to sell what you could do and work with other folks. And I think we ended up saving the owners on the order of more than $30 million in this effort and giving them a better product. And it's through all the tools that have been developed by many of the people in this room. And then also internationally. I talked with a reporter a few days ago, and they're like, well, we haven't had any Northridge 25 years ago. What's driving our progress? And besides the improved laboratory facilities that we have, it's also international collaboration. I mean, they have earthquakes in Chile and New Zealand and Mexico and Japan, and now we're much better set up to learn from those experiences. And so certainly those kind of efforts have been a big part of making progress. I'll skip over the video, it doesn't really matter. Steel frames. Certainly, I don't know anything about this, so I shouldn't say anything other than Tom Sable told me, and Jim Malley told me, we've made a lot of progress, and it's listed here. And I know this, in fact, because I see how I used to teach steel design in undergraduate, and I thought it was relatively simple, and now I see that everything's gotten a lot more complicated. But certainly, we've made a lot of progress on looking SAC project within Pier, and beyond with requirements for steel structures. I end up with a few challenges, and some of these have already been mentioned. System level response. I mean, almost everything that we did, or I did, as you know, if we design a beam, we design a column, we design a joint, we design a lateral system, and we often don't design the diaphragm or the gravity system. Everything's separate. And I think one of our big challenges is to look at system level response, and this has been coming about in more so in the last, say, 10 years, where there's a lot of interest in this area. And so we can do that through shake table tests. But some of the challenges there is they're very costly. And certainly they need to be large scale, they're three-dimensional, there's a cost of instrumentation. Another challenge is damage level. I was just in Japan last week for this test. And it was very interesting, but they barely pushed it into the nonlinear range because they couldn't afford to worry about collapsing it in their facility. And so that was certainly a challenge that we sometimes can't achieve what we'd like in a laboratory setting. Nor do we have the foundation and the soil and other parts of the system that are important. Data sharing can be a challenge, and I think funding is certainly a challenge to get funding for these type of tests. And so we need to pursue these, but I think if we, and collaborate internationally so that every test that gets done, we can learn the most from. And that's why the international collaboration, I think, is so very important. Another part of this that's been mentioned is system level response, but in not system of a single building, but in the bigger community scale. And so that's certainly important, if resilience, how do all these things work together? And I think there are challenges of how to take advantage of instrumented buildings in an instrumented city. Certainly we have a very important program here in LA to instrument buildings, and there are other programs, and we need to figure out how to take advantage of those in a framework that allows us to, when an earthquake or when some data become available, we'll be able to use it effectively. And there are challenges here associated with sharing data in private buildings, sometimes in triggered versus continuous data, and so on. So, and some of the more important things, I think, are instrumented density, but even more important, diversity. We tend to always have accelerometers in buildings, and often we're interested in strains or curvatures, and we rarely have that kind of information available to us. But certainly a huge opportunity that we have to look at. Performance goals, certainly, I don't probably need to say much on this, is that the goals of our current documents are really life safety, collapse prevention. I think as we look to the impacts of, say, Chile, New Zealand, and whenever California comes about, in Chile, I think the number of collapsed buildings was something like 0.3%. And as engineers, we'd have to say, hey, that's wonderful, we did a great job. But walking around Chile, particularly Concepcion, I didn't see a lot of very happy people. And our targets for performance, I think we really need to think about that more carefully. And certainly that's coming about. So I think we have to look at higher performance structures and particularly, again, existing buildings. As I said, everything's an existing building that's out there right now. And there are a lot of issues that we identify, and we're slowly identifying ways to improve that. Now, another challenge that we really haven't had to deal with in LA or California is as much related to repair. In New Zealand and Chile, they've had to worry about what to do with moderately damaged buildings. In New Zealand, I think it was primarily driven by insurance. Insurance dictated that most of them were going to get demolished and replaced. That's probably not going to happen as much in Los Angeles because of the level of insurance. But what is the capacity of a damaged building, and how do you evaluate it, and how do you make decisions related to demolishing a building or repairing it? And we really haven't started to really look at that problem yet. And that's one that I think we're certainly hope we can get some progress before a significant earthquake, because that's going to come up and have a very big impact on the economy and the ability for people to go to work. And another one is in terms of resilience. This has been mentioned. Mary talked about this. So I don't really need to talk about this very much other than we're slowly moving from this beam and column to a lateral system, to an entire building system, to a group of buildings, and now we're looking at buildings and interaction with transportation systems and electricity and water and so forth. There's certainly a lot of challenge there. I think one of my observations, one of the bigger challenges is with some colleagues, you go out and write a proposal and you pull a bunch of people in and you don't know where to send it because it's very collaborative and there's no program at NSF. In fact, recently Henry Burt and I, he tried to submit a proposal and was told, no, it can't go into this program and there's no place for it to go. So there's that part of it. And often with funding levels that are available, if you try to put together a big proposal, you find that your budget won't work. It's a budget buster. So you've got $1.2 million is the biggest budget you can put in, but in order to do the project that you've conceived, you probably need $3 million. And that's certainly a challenge that we're having trouble, that I don't think NSF and some groups have figured out how to fit into how we see research moving forward in the future. I think California has to step up as well. I mean, if you look at the peer funding, it has remained constant or even gone down since 1997. And certainly we have a lot of exposure in California, and the level of funding just hasn't been there in terms of supporting peer. So outlook overall, it depends on your viewpoint. Whether you're an optimist, a pessimist, I don't know if we're allowed to be a realist anymore. Not sure how that works, but the optimist in me says, well, we've made tremendous progress. Look at retrofit standards and guidelines and new buildings and databases that are available to us. I mean, we've made tremendous progress. The pessimist in me says, well, we've done that over the last 25 years with more focus on earthquake engineering, and now we're a more mature field. And we face the challenges that I was mentioning earlier. So maybe our progress will slow substantially. I don't know. The realist in me says, well, there'll be an earthquake and maybe that will change a little bit once there's some motivation. But I am concerned that the general public thinks things are going to be much better than we think they're going to be. Everyone thinks their building's earthquake proofed, or even if it's the 1950s building because it survived the San Fernando earthquake. Those videos of Mexico are really telling. Those buildings, most of them survived the Mexico City earthquakes, but they didn't survive the last one. Everything can be a little bit different. So we certainly have a lot to do. With that, I'll close, and thanks for joining us here at UCLA, and thanks for your attention.